than the largest eigenvalue of B. Even the smallest eigenvalue of A will be no less than smallest eigenvalue of B. Okay. So this is this fold property. Any questions in understanding this statement? Right. That's proof. Okay. The proof of first and second, they are similar. So we only prove the first one. Okay. Only prove the first one. So now we have like A greater equal than B. We show that is if and only if its eigenvalue is that, right? So A is greater equal than identity. We know this is A minus I is a PSD matrix, right? It's a PSD matrix. Then because A here we assume is a Hermitian, okay? It's a Hermitian. So we can have it's always unitary and diagonalizable, right? So we can have EVD, right? Suppose EVD of A is V lambda V Hermitian. Okay. Then this V is unitary and lambda contains this lambda 1A, lambda 2A to lambda MA as a diagonals, right? It's like this, right? Then we apply this EVD, so we can V lambda V Hermitian minus identity. It's a PSD, right? It's a PSD. Then we have used this trick before, right? So because VV Hermitian is identity, so we can replace this identity by VV Hermitian. So this is get this, right? Get this. Now, if you recall our transformation property, right? This is like A, B, B Hermitian, and here V is unitary. It's a unitary, so it's square invertible, right? So the PSD of this, the PSD of a whole guy, right, is equivalent to a PSD of the guy in the middle. Okay, so this is right. So this is by the transformation, right? So this is PSD, right? And this is diagonal. You know, right? It's diagonal, and his diagonal is the eigenvalues, right? Itself eigenvalue. So this is if and only if lambda IA minus the 1 is greater equal to 0 for all, right? Because lambda and I is a diagonal, right? It's diagonal matrix. So its diagonal elements are his eigenvalues. Then its PSD means its eigenvalues is greater equal to 0, right? So we prove this, right? So I prove this. Okay, so so this give in some for example in some optimization or some engineering problems, you might have some constraints, right? If you have some constraints on the eigenvalues, then this actually give us your alternative expression, right? To express these constraints on eigenvalues using this matrix inequalities. Okay, matrix inequalities. Then this is nonlinear in A, right? Eigenvalue is a nonlinear function, but here this representation is linear in A. Okay, so this can be a much convenient in some applications. Okay, to represent in this way. Okay, so then let's see how to prove the third one. Okay, actually it's similar. Proving the third one is similar to the first one. So here we actually see the insight. The insight is that you use SVD, right, to transform this matrix into scalars, right? But the scalar is in its eigenvalue value domain, right? Then once in the transform into the scalars in terms of eigenvalues, then you can apply this regular inequality numbers, right? Okay, so that idea will be, let's see, we can use the proof, the third property. Okay, any questions for this proof? Okay, let's see how to prove the third one. Okay, now we assume that A, B are both PD. Okay, both are PD. So which means that both are invertible, right? A, B are both invertible. Now we consider that A is greater equal than B. Okay, so now we have A is greater than equal than B, right? A is greater equal than B. Then this is equivalent, right? Saying that A minus B is a PSD. Okay, it's a PSD, right? Then we are going to use that. Okay, A is PD, right? So A is PD. So we can have square root. Okay, we can have square root of A, right? So A is PD, so we can square root, have A square root, A square root, right? Is equal to A. So we can express A by his square root. And note that these, because A is PD, so square root is also PD. Square root is also PD. So, sorry, not necessarily PD, but it's invertible. Okay, it's invertible. Because the square root may not be Hermitian, okay, but it's invertible. Okay, right. This must be invertible, right? Because its determinant equal to a determinant of A, and A is a PD. Its determinant is non-zero, so its determinant is non-zero, so it must be invertible, right? So A square root is invertible. Okay, so we can write in this way. Okay, so we can B here, right? We can multiply A square root and the inverse of A square root on the left hand side, and also in the right hand side, we multiply A inverse square root and the A square root. Okay, so then we can take the A square root to the both sides, here and here. Okay, here and here. Okay, then again, you apply transformation, right? This A is square invertible, so this PSD implies the PSD of the guy in the middle, right? So this is A. Right? Then here, right, this means that this matrix is smaller or equal to identity than by the previous property 2, right? By the property 2, you know that these eigenvalues of this matrix is less than 1, right, for all. Right? And note that, right, the eigenvalue of A, right, this matrix, right, this matrix, or look at a general case, the let me see. Yeah, anyhow, yeah. So here you see all the eigenvalues less than 1, right? So this eigenvalue of this matrix, right? This matrix, right? Is actually is 1 if you consider its inverse. The inverse of this matrix is A square root B inverse A square root, right? This is the inverse of this guy, this matrix, right? The inverse matrix, right? You know that A, B inverse, if both are square invertible, is this, right? So the inverse of this matrix is given by this, right? Then what's the eigenvalue of this one and this one? What's the relationship? Right? By EVD, right? If A has a eigenvalue, it's like this, then what's A inverse will be V lambda minus V omission, right? Right. So the eigenvalue of A, right? Suppose lambda 1 to lambda m, then what's the eigenvalue A inverse? Will be inverse of lambda 1 inverse lambda 2 inverse lambda m, right? So these eigenvalues, right, we can write as the eigenvalue of the inverse matrix, inverse, right, less than 1 for all I from 1 to, right? So this is equivalent, right? So these eigenvalues of this matrix, right, is the inverse 1 over, right, 1 over the eigenvalues of the inverse of this matrix, as I put here, as you can see, right? What's the eigenvalue A inverse is a inverse of the I lambda, right? 1 over lambda, lambda I. So then we have this, right? Then this implies these eigenvalues of this matrix all are greater equal than 1, right? Because 1 over it is less than 1, it's no larger than 1. So it means this, you multiply this to the right hand side. Each of them is greater equal than 1. So which means then again by property, by the first property we already show, which implies A square root B inverse A square root or no larger than 1, right? So which implies this matrix is greater equal than identity, right? So here, right, in this one means these eigenvalues, right, in the denominator is greater equal than 1, right? Then by the property 1, right, by the first property we just proved here, right, just prove here, means these matrix is greater equal than identity, right? Greater equal than identity. Then this means A square root B inverse A square root minus I is a PSD. Right. Now again, we can multiply here A inverse square root right. Here we can do is here we multiply A inverse, right, inverse square root multiply A inverse square root, right? And here we apply a square root. You see, right? So, okay, maybe I should do this way. Right? You can write this identity as a square root, a inverse square root, a inverse square root, a square root. Right? Or here I write a inverse. Right? This is identity. Right? You can write identity as like that. Right? So then this is a square root b inverse minus a inverse a square root is PSD. Right? It's PSD. Then again by transformation, right? This square invertible, this implies the guy in the middle is PSD. Right? Then which implies B inverse square equal to A inverse. And done. Okay. And done. So you see the proof, right? The idea of the proof is trying to, right, convert to the eigenvalues, right? Using this diagonalization, right? Like this property, eigenvalue decomposition. So we can get this. Then do this inverse, right? On this domain of eigenvalues, right? And then here is to convert back to matrices, right? This step you see is convert back to matrices. Convert, yes. Yes. You mean here? You always can multiply from left-hand and right side, but the key is that whether this will be PSD, right? So this matrix, we multiply this and this, we always can do that, right? But this new matrix is a PSD or not? Okay. Yeah, that's a transformation. We have a theory 3. We check out last week. Transformation. If you want equivalent, then this need to be square and invertible. The matrix you multiply need to be square invertible. Okay. Check out this theory last week. Okay. Any other questions? 所以要复习啊，你不复习的话就跟不上了。Okay. Then the last one. Okay. To prove the last one, we need to know more. Okay. To prove the last one, we need to know more properties. Okay. So let's keep this in mind. Okay. So we are going to prove this. We're going to prove this. A is greater than equal to B, then it's older the eigenvalue. Okay. Also satisfy this inequality. Okay. So in order to for that target, we need to introduce more terms. Okay. 有没有再多？没有问题了是吧？No more questions. 这样子我就一直往前跑，一直往前跑。Okay, then we need to introduce variational characteristics, variational characterization. Okay. So then we need to know more ways to represent an eigenvalue. Okay, if we want to prove these properties. So this is variational characterizations of eigenvalues. Okay. So this theory, okay, is called Rayleigh's theory. Okay, which says that if A is a Hermitian matrix, okay, then the largest eigenvalue of A, okay, for example, if we order lambda 1 to lambda n, then lambda 1 is the largest, okay, the largest eigenvalue is equal to, if we consider this objective optimization problems. Okay, you say the largest eigenvalue is equal to if you maximize the quadratic form. Okay, the quadratic form. Okay, of course, then here we have subject to this constraint to a length of x, otherwise it goes to infinity, right? It could be goes to infinity or what. So you need to constrain the length of the variable x. Or this is equivalent writing this equivalent, write a problem like this, right? So this is equivalent problems. And similarly, minimal eigenvalue, the smallest one, okay, the smallest eigenvalue, then is you change this maximization problem to the minimization problem. Right. Okay. Actually, this is not difficult to see, right? You just apply the eigenvalue decomposition, then you see. So any questions in understanding this statement? Okay, so largest eigenvalue is you. So this is called Rayleigh quotient. Okay, this is there's a term called this Rayleigh quotient. Okay, it means that term is called Rayleigh quotient. Anyhow, 这是一些名词而已。Okay. Right. So you look at this. If you know how, if you understand this, you can understand this, right? Because you look at this problem. right? You look at this Gini function, right? Then you apply the EVD. Okay, you apply the EVD. Okay, where V, suppose each column is V1 to Vn. Okay, V is unitary, right? Lambda is lambda 1 to lambda m diagonal. Okay, then suppose lambda 1 is the largest. Okay, so lambda 1 is lambda max. Okay, suppose lambda 1 is lambda max and no less than lambda 2. Right. Then you substitute this into here, right? So you see this is x Hermitian V lambda V Hermitian x. Right. And for this we can write, right? We know that we can use this outer product expression. This is summation I from 1 to n lambda I Vi Hermitian. Right. A can be EVD can be written this way, right? So then this is summation I from 1 to n lambda I, right? Vi Hermitian x squared, right? Then of course, right, this is no larger than if we replace lambda I by lambda max, right? Because each of them are small, no larger than lambda max. Right. So because this is the largest one, the smallest lambda max, right? So then this is lambda max. A, and how about this term? This is x Hermitian V Hermitian x, and this is VV Hermitian is identity, right? So you get lambda max x 2 known squared, right? 2 known squared. So we obtain that x Hermitian ax divided by x 2 known square is no larger than its largest eigenvalues, right? So you see the real quotient, the largest is the largest eigenvalue. And if we want to show that its max is equal to the lambda max, then you need to show that this can be attained. This upper bound can be attained. Attained by which x? This can be attained by which x? Right? X is V1. Right? X is a eigenvector associated with largest eigenvalue. Right? Then this is largest eigenvalue. So then let's prove this. Right? So we first show the largest value of this Rayleigh quotient is lambda max. Then it can be attained. Right? This upper bound can be attained when x equal to V1. X equal to the eigenvector associated with lambda max or lambda 1. Right? So then let's prove it. Then similar for the minimal is the same, right? Minimal just change here to greater equal, and here is minimal. Okay, so eventually we get that this Rayleigh quotient, right? its upper bounded by its largest eigenvalue and lower bounded by its smallest eigenvalue. And here again, this is attained by when x equal to Vm, the eigenvector associated with the smallest eigenvalues. Okay, so we have this inequality. Any questions here? Okay, so this tells us alternative, right, representation for the largest and smallest eigenvalues. And the natural question is, then how about the others, right? How about the second largest eigenvalue? How about the third largest eigenvalue? How should we represent, right, those guys? Okay, so this is for largest and for the second largest. Then how about the others? Right. Then this is this Cohen-Fisher theory. Okay. So then this Cohen-Fisher gives us a more general expression for the eigenvalues, and for those in the middle. Okay, those in the middle. Particularly, it says again, we have A, right? A be a Hermitian, and his eigenvalue are ordered from lambda 1 to lambda n. Okay. As eigenvalues. Okay. Then this Cohen-Fisher says for the case, for lambda k, the k is largest. Okay, k is largest. Eigenvalue of A can be written as a min-max problem. A minimization and maximization. What's these maximizations? The minimization is given k minus 1 vectors, w1 to wk. Okay, so in outside we have k minus 1 variables. Each of them is Cn. Then given this w1 to wk minus 1 in the inside, we again consider the same quadratic form of Rayleigh quotient. Okay, but there's an additional constraint is that this x, okay, is subject to orthogonal to the w1 to wk minus 1. Okay. So for this is the Cohen-Fisher theorem. The k's largest eigenvalue can be represented as a min-max form. The outside minimization is given. Okay, consider k minus 1 vectors w1 wk minus 1, and given this in the inside, we still consider the same Rayleigh quotient, maximizing the Rayleigh quotient, but x need to subject to the orthogonal to this w1. Right, this look quite complicated, but you now reduce k equal to 1. Right, you look at spatial case. How about k equal to 1? So that means the largest eigenvalue, right? If k equal to 1, then this disappears, right? You don't have this. You don't have this. Then this part is really rich, tells you, right? So you see that this is more general, right? It's more general and incorporate it's really rich. Is that okay? Right? So when k equal to 1, this reduced to this, right? Reduced to this. And how about the other one? If k equal to m, k equal to m, k equal to m, then reduce 不了，对不对？reduce 不到这里 ，right? K equal to 1, that can reduce to here, but when k equal to m, that does not reduce to this, right? So there's another equivalent representation is, so can be written as min max, also can be written as max min. Okay, also can be written as max min. And for max, now we need to consider lambda k plus 1. So this here is w k plus 1, k plus 2 to wm. Okay, so here we have m minus k vectors here. Now again, here inside, we still minimizing this relay quotient. But subject to the x is orthogonal to this m minus k vectors. Okay, so here's from k plus 1 to m. So then when k equal to m, then you look at this max min form. When k equal to m, then here disappears, okay? Because here's from k plus 1, k equal to m. It means the max can be removed, okay? Then know this. And reduce to minimize of this radial quotient. Then reduce to the second one. Okay. So this gives us this two variational characterization. So it's called variational characterization of these eigenvalues. Okay, can be written as min max or max min. Any questions? So first, understand this statement. Okay, this tells us how we can express the case largest eigenvalues of a Hermitian matrix. Okay. Okay, so then let's see how this can be proved. Okay, so we will prove this part, prove the min max part. Okay, the max min part can be proved in the same fashion. Okay, the same fashion. So let's just go through this min max. Okay, so we will prove two items. First is that, so first we will show the inner maximization part. Okay, so given arbitrary W1 to WK minus 1. Okay, given arbitrary W1, WK minus 1. Given this, we look at the inside. So that maximization problem. Okay, so now it's subject to the orthogonal to WK minus 1, WK minus 1, and this. Right. First of all, we will show that this is great equal than lambda k. Okay, so this is for any W1 to WK. Okay. For any W1 WK, so I'm sure this is great equal to lambda k. Right. Then you see the inside is great equal to lambda k, and you want to show that it's minimize. You minimize this term over W1 to WK minus 1 can be equal to lambda k. That means the next we need to show is we need to find out a set of W1 to WK minus 1. Right? When you substitute that W1 to WK minus 1 here, then you attain the lambda k, which means this lower bound can be attained. Right? Can be attained. So second one we show is actually the second one is easier. Okay, it's to show that this quadratic form when x is orthogonal to the previous the eigenvectors associated with previous k minus 1 eigenvectors. Okay, so W1 equal to V1, WK minus 1 equal to VK minus 1. If we choose this particular W1 to WK minus 1, then this ratio, Rayleigh quotient, is equal to lambda k. Okay, the second one is actually much easier to show. So by show this, we then prove. So it's okay. Understanding these two. If we prove these two, then we prove this. Right? Is that okay? 对不对？是不是啊？我不证这两个是不是就证明那个了？是吧？这个逻辑 OK 吧？ Is that okay? So if I prove these two, I show this, then I show this, and that's equivalent. I prove this. Right? Equivalent, I prove this. Prove that the inside objective function is lower bounded by lambda k. Then we show that, right? We show that by letting or by choosing Wi equal to Vi, I from 1 to k minus 1. Right? Wi equal to Vi for I from 1 to k minus 1. When for this particular W, then we equal to lambda k. That means this lower bound is attained. Right? It's attained. So we prove that. We prove this statement. Okay. So let's first prove 2, because 2 is easier. Okay. Let's check out 2. Okay. We show that for this, when x is orthogonal to V1 to Vk minus 1, right? This is lambda k. Right? So right, we consider this. Then by apply EVD of A, right? By apply EVD of A, we can write A equal to summation I, lambda I, vi, vi, Hermitian. Right. So this is max subject to summation lambda I, vi, Hermitian x value square over x2 known square, right? We just substitute EVD of A, right? Then x is orthogonal to V1 to Vk minus 1. So you see in this summation, right? This summation from 1 to m, right? So you see for I equal to 1 to k minus 1, this inner product will be 0 because x is orthogonal to it, right? Will be orthogonal to it. So we can change this, right, to the summation 1 to m. No, we can change it to, right? We can change it because from 1 to k minus 1, this inner product will be 0. So here, what that is from I from k. I is from k, right? It's that, right? Because I from 1 to k minus 1 is this inner product is 0, right? So this summation is equal to, we only consider I from k to m, right? From k to m. And this is lambda I. Right, it's equal to this. What is maximum value for this? By Rayleigh, right? Rayleigh. Because for this is a quadratic form of a new matrix whose largest eigenvalue is lambda k, right? It's lambda k, right? So this is equal to lambda k, right? You just or you can further prove this by following the same proof of Rayleigh. You see its upper bound is lambda k, and that upper bound can be obtained when x equal to vk. Okay, when x equal to vk. Okay, so you see this is achieved when x equal to vk. Okay. Actually you only need to keep in mind this expression. This expression tells a lot. Okay, this means that for Hermitian matrix, because it's unitary and diagonalizable, all these VI are orthogonals. Okay, can be written a summation of m rank 1 matrices. Okay, weighted by its eigenvalues. And each of these rank 1 matrices, they are orthogonal to each other. Right? So when x is limited to orthogonal to the v1 to vk minus 1, right, then you can eliminate the first k minus 1 components, right, from these summations. Then this is, for this one, its largest eigenvalue is lambda k, not lambda 1, because lambda 1 to lambda k minus 1 is already excluded, right, due to this orthogonal constraints. Okay, excluded. Right, so now the largest become okay. So we prove this second statement. Okay, put it second statement. Okay, then let's show the first one. If it's arbitrary, okay, it's arbitrary, then it's still no less than lambda k. Okay, let's see the. Okay, let's check out the first one. Okay, so now we consider the x is orthogonal to arbitrary w1 to wk minus 1. Right. Again, we use EVD. Okay, it's a EVD. Okay, we apply EVD V lambda V Hermitian to A. Okay, suppose EVD. Right. Okay, then here I do a change of variable. I let y define y be V Hermitian X. Okay, do a change of variable. So y, let's define y to be V Hermitian X. So X, right? So X can be written as right Vy, right? So X can be written as Vy. Then we can write this quadratic form in terms of y. Right now V Hermitian X is y. Right. So it becomes y Hermitian lambda y over right x2 norm square is equal to y2 norm square, right? Because V is unitary. Right. So we can rewrite it in terms of y. Now the constraint need to rewrite in terms of y as well, right? So here is orthogonal, right? X is orthogonal. So X is orthogonal to Wi, right? One of the Wi, right? Now X, so which means is X Wi Hermitian X equal to 0, right? Now X, we use Vy to represent it. Now, so this becomes W Hermitian, right? Vy equal to 0, right? Because this. So now the constraint, right, becomes y need to be orthogonal to Wi Hermitian V, right? Or V Hermitian W. So here, right? So here needs to be. Here now it becomes y is orthogonal, right? Y is orthogonal to V Hermitian W1 to V Hermitian WK minus 1. Right? I'll change it to this. Right? See. So our goal, right, is trying to show that the minimum is lower bounded by lambda k. Okay. Then here we, in order to make out this, okay, work out this, we add one more constraint to a y. Right? So the original constraint is y is orthogonal to this guy, right? Now we add another constraint, is that we assume that y k plus 1, the k plus 1's entry of y to yk plus 2 to the last entry, we enforce it to 0. Okay, so we add more constraint on 1. Then this is a maximization problem, right? Y original is subject to this constraint. Now this constraint becomes more stricter, right? Right. So this is smaller because we have add one more constraint. So this maximum value will be no less than this, right? Because this maximization problem has a smaller feasible set than this one, right? Because here we add one more constraint to it. Is that right? Okay. But adding this is a minor question, a subtle question, is whether this is feasible. Will this be empty? Right? If this is empty, then this is meaningless. You cannot have this. So you need to check out whether this is non-empty, right? So this is quite subtle. You can check out this, right? You see, because now you enforce, right, the last n minus k entries of y to be 0. So in this set, the inner product y with any of these vectors, right, can be, you only need to consider the first k entries, inner product first k entries of y, because the last n minus k entries are 0, right? So this can be, this set, right? This set is equivalent, saying this. Okay, the first k entries of y, inner product with the first k entries of this vector, right? And so on. Right? And this need to be a 0 vector. So that is equivalent, this constraint tells us, right? You consider only need to check out the first k entries, right? Because the last n minus k are 0. Right? The inner product of this one with this one should be 0. So you see this is what? This is a k minus 1 times k, this matrix dimensions, right? So then this implies, and this y is in his null space. So you see is dimension of null space is right, is greater equal than 1, right? It's greater equal to 1. So this is non-empty. So this implies this is non-empty. Okay, it's non-empty. Because this is a fat matrix, right? A fat matrix. And y is in null space. So this is feasible. Okay, this is okay. So this is valid to add that additional constraints on this. Okay, so for this new problem, because now y, the last n minus k entries are reduced, right? Are enforced to 0. Enforced to 0. Are enforced to 0, right? So this is equivalent. We consider only the first k entries, right? first k entries. Let me see how do we call it? Okay, we can keep it. It's okay. Okay, I keep it the notation. So this is the sameness, right? So this one is the sameness. The y is orthogonal to v Hermitian w1 to v Hermitian wk minus 1, right? Okay, and the last k entry is 0, right? And we know that this problem is also equivalent if we put this, right? We remove this, put this to here as y2 norm square equal to 1, right? This is the same, right? The same we maximize this quadratic form and subject to the 2 norm of y equal to 1. Okay, so here the 2 norm square equal to 1 and is last n minus k is entry equal to 0, right? So now this is equivalent. The first k elements is summation equal to 1. Okay, summation equal to 1. Okay, right? And now the objective function is but because the last n minus k entries are 0, right? So here this is 1, 2, k. Okay, I need to consider 1. Okay, is that okay? So this is the same. Right? Then it's similar to we prove the Rayleigh-Ritz, right? So this is no larger, no less than, right? Lambda k. Okay, because lambda 1 to lambda k is smallest among lambda 1 to lambda k. This is no less than lambda k. And this is achieved, right? This is achieved by choosing y equal to 0, 0, 1, right? So we get this lower bounds. Okay, we get this lower bounds. So this may not be necessarily achieved by this. May not be necessarily achieved. Okay, but it's lower bounded by this, right? Because this is, see, this summation, right? This coefficient, these are coefficients of this, right? Coefficients summation equal to 1. Each coefficient is non-negative, right? So this must be no less than lambda k. 这没有问题吧？你10、5、1这三个数 non-negative 的权重加起来，对不对？最小值就是1嘛，组合的最小就是1嘛，不可能比1更小嘛，对不对？懂意思吗？这些数，然后这些系数都是非负的，它这个最小值一定就是这个组合最小值一定就是这个 lambda 1到 lambda k 里面最小的，就是 lambda k。Or this is called convex combination. Okay, this is called convex combination. This coefficient summation equal to 1 and non-negative. Okay, and it's minimal. This minimal is equal to the smallest value over lambda 1. Is this okay? Right? So this one is no less than lambda k. Of course, the maximum of it equals no less. Okay. Right. Yeah. What's give me this? Here is not necessarily being a 10. So this may not be equal because the y may not satisfy this. Okay. So if without this, then we know that obviously you can choose. You know what is optimal y. But without this, then we may not attain this. But we know this will be lower bound.
If we write from lambda k equals to mu by x by fx, fx lambda, fx w, replace x h x over the sum of x. So now one to
Yes, yes, please after the class because I don't get your question. Yeah. Okay. Yeah, we talk about later. Okay. So this is a lower bound, but it may not be a 10. Okay, because we have this. Okay. But the second statement tell you it can be a 10 if W1 equal to V1, W2 equal to V2. Okay, and WK minus VK. Then it can be a 10. Oh, any questions about this? Yes. No, this is equivalent. We can put this to here, right? We say in a relay quotient, this problem is the same as this is the same, right? The optimal value will be the same. The x will not be unique. You can arbitrarily scale x, right? But the ratio will be fixed, right? So without loss generality, without loss of optimality, you can constrain it. Yeah. Yeah. The value, the optimal value will equal to the optimal value. Okay. This is not the same, but maximize the same. Okay. The optimal will be the same. No, sorry, this is an arrow. 这是个箭头，你搞错了。Okay, this is equal to 1, not less than equal to 1. It's equal to 1. Okay. Okay. Any questions? Okay, then I might stop here. Okay. So based on this Coulomb Fisher, then we can use that to prove when A greater equal than B, then lambda IA greater equal to lambda IB. Okay. We'll do that next week.
这个4现在还证明不了吗？
对，就是下一次要证，就是我要用这个东西来证。
就是我感觉第二次作业的那个第一题里面有。